Thanks, Kevin, for the introductions. And also, first of all, I would like to thank the organizers for inviting me here, especially, again, Kevin and also Melissa for taking care of the invitation and documents. Today, I'm going to present the methods of machine learning potentials based on our approach that we use artificial neural network. And I would like to correct that I'm not the first one to really apply neural network for this kind of application, but already from many previous works, but we just develop more to make it more transferable and also make it easy for many different types of materials. So today I will separate my talk in two parts. So the first part, so I will I would like to discuss like a theory and also how we can make it easier. And also the second part, I will discuss more like application. Again, today I will mainly focus only on machine learning potentials based on artificial. Just to let you know that everything that I'm going to talk about, this is based on atomic simulations. But as you know, right, atomic simulation, I mean the y-axis is like a system size, and also this is x is the method or the application. I mean that we would apply to. Depending on our research, right? Like with theory or with accuracy that you would like to have. So start from like a small number of atoms that we can use already as a DFT, that we could use mainly like also for electronic structures, and also can treat like crystal structures. But if we would like to study and make it like closer to experimental scale, we need larger number of atoms, and also including, for example, like oscillation or many different complexes. In this case, even many applications like nanoparticles, and including oscillation. This is, for example, like a water, or even larger scale, like a very complicated interface and also nanostructure. And not only this, if you really want to go to realistic conditions, we have to also, for example, like in our atomic simulation, in like molecular dynamic simulation or Monte Carlo simulation for extensive sampling. And this also includes like temperatures or pressure. As I mentioned, right? For example, like the complicated electrochemical interface. For example, is very challenging for the simulation. What we would like to describe, for example, this is like a simple cartoon that I show in the, for example, like in the reaction mechanism of catalyst in the very complicated surface that would have in the experiment, and also including molecules and also very complicated interface in this case, or even not the pure similar like a solid liquid interface, and also even in the interface itself or complex, even sometimes also solid, but different kind of materials. You already have different kind of like a structure, distance. I mean like a very different and very complicated. So I would like to check here if we would like to have really accurate potentials. So we need, for example, like we would like to have potential can describe bond breaking and forming in the same time. Also that includes gas phase, liquid, solid, and interface. And also sometimes is non-ideal and also contain a lot of like defects, and also include some kind of like solvent effects and also electric field. The current state of our methods right now, if we talk about like to describe this kind of properties, the for large scale, right? The classical molecular potential that cannot really describe bond breaking and forming. And if we want our accurate word principle, it's very difficult to treat all kind of properties that I just mentioned here. And just would like to make a list what I just said before. The potential for materials the empirical potential is that efficient, and also if we want to represent very complicated, right? It's quite, the functional form is quite simple and also not very, not reactive. And also if each type of potential also create in the way that it can describe only some type of materials, which it not even, the transferability. For example, we have, for example, like for gold, we would like to have like in solid. We probably have different lattice constant, or the parameter is different from melting gold, for example. That's why I'm saying like the empirical potential only can fix high of parameters. And then the next one, the first principles, or the ab initio potentials. It is general and also predictive, reactive, and also can describe chemical reaction. But how to explain, like sometimes it's also functional, it's also limited. For example, if you want to use first principle methods for metals, and also including some kind of organic molecules, which you don't need the same functional described in the same system. And also, if we want to go to very large scale, it's very expensive. Oh, by the way, I will share all of my slides here with you. I already sent my PDF. I already to maybe the information. So can we use machine learning to help us to accelerate our need, or to use it to extract information from accurate first principles? So what we would like to do is that this is the state of atomic simulation. We know that first principle methods, right, can produce accurate energy and forces, but quite expensive. And for the empirical atomic interaction potentials, it is efficient, but most of the time it's not reliable for all kind of systems that we would like to use it. Can machine learning help us? So the idea is that we would like to train efficient machine learning model to reproduce the properties from first principle results. So what we need, also Luca already mentioned that the descriptor of atomic structures that we could use as input. There are so many ways to use as a descriptor. So I will also discuss today what we are using. So what we want to have, for example, like the model for energy and forces, I would call machine learning potentials, and all kind of the structural properties relationships, which we can use it for classification or interpolation. For potentials for materials, right? Many methods that they use it based on ab initio calculations. How the idea or the framework that we could have. For example, here we have a set of reference calculations. For example, like a DFT calculation, and then we extract information here. For example, like a bond angle or energies and forces, or even charges here. And then we use machine learning interpolate, and then we construct potential energy surface, and then we direct use in MD or MC or other tool that you would like to use it for your simulation. This way we will get efficient and also accurate for in this application. But the way that we look at like a reactive, this is also depending on the approach. The methods or our approach that I'm going to talk about today, we are using artificial neural network for the interpolation. Why a neural network? Because easy and also it can really highly fit the reference data very accurately. And also thing is also that there is no need to know any functional form of your potential energy surface that we can use it. I mean, like you just need to find a way to get the descriptor. And in this case, we will get a reactive and also full dimensional. I will explain in how we find a way to say this in the next few slides. Before to go to the detail of the methods, I would like to just give a brief, like some kind of like references that you could also look. So neural network that we can use it in this case that we use is for continuous function, and this, for example, in these 3 references that I think are good, look at it, and also I mean this kind of a method that we can use it to approximate for high-dimensional functions. And our approach, we use neural network to approximate the potential. Slides, I'm showing a very simple feed-forward neural network. There are, on the left-hand side here, there are 3 layers. The first layer is the input layer. The second layer is the hidden layer and output layer. How we can get the potential energy surface or energy or forces that we want to use it for our application, like in MC simulations, right? You can either look at on the left-hand side or looking at the equation here, the total energy expression analytics, like Luca also discussed from the previous talk that I'm also showing here. How can we get this output? So all of the layers here, they are connected, which they have like the square. They have physical meaning. Output, this is the energy and forces. The input layer here, they are atomic structures, like geometries, that we can have like a bond or angle or many-body interaction here, which you can get, for example, in your when you run the FT, right? You also need to prepare like a geometries, which you also can have like a XYZ coordinate. And then later, all of the layer here, they are connected. And in each layer, we have here the square and circle we call nodes. Here they are nodes, which they are connected with the black arrows here. They are neural network fitting parameters. All of the nodes, they are connected to each layers. So how to get, again, the output? First, here are number from the input layers multiplied by, here I call the weight, value or the weight parameters. And here, number, like for example, from here to here, this is like A01 or A11, and so on. And all of the number here, we sum up, and before we move it or go forward to the hidden layer, we apply, for example, like a nonlinear function. And usually we use like a sigmoid shape or hyperbolic tangent or cosine. It's depending on your application that you are thinking. This can be like a nonlinear function, right? And here, after we sum up, and then we get hidden layers. From hidden layers to the output layer, we use this number again and multiply it. But in this term, to go to the output, so we don't use nonlinear function. We just sum up as a linear, make it easier. This is just to show example of how we look at and get the output. In this case, I show very simple parabola that we have like a x as the x-axis and y, this is x squared. So we have, for example, here we have black diamond, is it like a reference of the parabola. And then we have a neural network as a red line here. In this case, we have only one hidden layers and 2 nodes. And each node here, for example, the blue line, you will see here, I combine only two nodes with hyperbolic tangent here. You can see clearly this is the actual or the real neural network fitting. The green one, also the second one here. And then we combine with the bias node, which is just a number to shift to the right position of the potential energy surface. Then we sum up here our parabola on the right. And this is just to show very simple, very small fitting. That after a few iterations, that our neural network already can fit the parabola curve accurately. So we use this idea and apply to a quite simple model. For example, in this case, we test to look at water dimer. On the left-hand side, this is to show the, for example, in this case, the black diamond, this is the DFT reference data of the two atoms of oxygen 1 and oxygen 2. And in the same time, we also can do force fitting. On the right hand side here, we show the same. And the red, this is a neural network fitting. At the beginning, we have like a random weight parameters. It can be anything. Then after minimize, our neural network potential can represent, for example, reference data accurately. So you can see both, like in the same time, energies and forces that you can see very represent the reference data very accurately. And for the forces, you could use it. In this case, so we can see that neural network can learn functional form of the potential energy surface here. Before we move on, yes, I also not for very high dimensional. This is the conventional neural network. Actually, it is not yet transferable for all kind of system, because so in this part, neural network still have some kind of like dimensional, and also, for example, if the input of atomic coordinates, for example, it can only use for some specified number of atoms. So therefore, we now try to think like how we will make it type of atoms, type of like solid and liquid. So in this conventional neural network potentials still not yet replacement for interatomic potential. If you have any questions, anytime, and also ask me questions during the talk. Here, so neural networks still not yet automatically invariant with respect to translation and rotation of the atomic structures, and also not even because we just need a number, right? Even when we exchange the two, for example, like water, we have H2O, right? And if we change the H1 and H2, kind of not yet not understand that. That's why so we would like to do like how can we construct, or how can we develop a universal atomic energy functions. So I would like to look back, for example, like maybe already familiar with embedded atom models or EAM potential here. So this is the very simple notation that I show. This is the total energies of atomic contribution of a structure here. It's come from the summation of the energy of many atoms in each structures. And this is similar way that we would like to have is for the EAM total energy, which is for the EAM of atomic energy is come from two terms. The first actually here, this second term is come from the pair potential, or like I and J here. And the first term is come from the contribution of the charge density, which is embedded with the functional. In this notation, or in this atomic energy function, it is contained of the physical, but actually not yet flexible, because different type of like EM potential that can use only some kind of applications. So this model is not yet appropriate for every kind of the structure and also chemical species. So we would like to use similar idea of EM and have machine learning to help to make it like potential. So in 2007, Behler and Parrinello demonstrate that how to apply this method by using neural network. So I just would like to make it the step by step, show you how it works. The total energy that proposed by Behler-Parrinello, that is the sum of atomic energy. Nice, right? And we use neural network to represent atomic energies, I. And now the input, we try to make it like an invariant respect of the local atomic environment. And then we can use it now to replace mean of interatomic potentials. This is now how high-dimensional neural network potentials that Behler-Parrinello have. The total energies now is come from many or some of each atomic energies. And each atomic energies come from atomic neural network. And I already explained before how the simple and normal standard feedforward neural network work. But before that, the input layer here, that this is the atomic position that it's XYZ coordinate, right? It's transformed to a set of many body functions which should describe a local of each atom, which we could also call like a fingerprint in this case here. And usually for the materials that we are interested in, we use a radial cutoff of like a 6 to 8 angstrom. This is the first proposed by Behler-Parrinello in 2007. And now we are thinking like, okay, what about, it was like a for short range. And we also think like how we could use the same or similar approach to describe like for many chemicals or for multicomponent, also capture like long range energies. So we are thinking like some steps. So first, we would like to take care of many chemical species. So electrostatic interaction may be important, right? We should include it. And electrostatic interaction, this is to capture the long range. And actually, this is also cannot really decompose electrostatic energy to atomic contribution, but it can calculate it. Anyway, there is no unique way, but we could try, we could do. So we're just thinking like now how to train a separate high-dimensional network for also atomic charges. And we use similar idea of the Behler-Parrinello, and then we include a second set of neural network, but based on atomic charges. And now our new new diagram here. We have the total energies come from two parts, like energy from the short range and also energy from the long range. And this is, I already explained before, and in this term, here we include the electrostatic term, which is, for example, get from eval summation. And after some applications that we use the diagram of the second methods that I just explained, which it can use very well for multi-component systems. In practice, we found out that for the electrostatic interaction, is that actually it's already screened in the condensed phases. We also test and try and also work and check the output. So we found that actually if we use the same diagram like a Behler-Parrinello that proposed in 2007, but if we increase it, like the R cut larger, for example, like usually we use like 8 angstrom, we could use like 8 to 15 instead of the short range. This also could already capture the long range interaction. But I mean, but it's many atoms in the radial cutoff. Yeah, we already test with many molecules and also many different. And now, our high-dimensional network now can work for many different types of materials, even in the same time. You can describe like a isolated molecule. In this case, I just show the copper dimer, that we use the same potential that can describe, for example, like copper gold alloy, which is many different types of the crystal structures. For example, in this case, I show a very simple model, for example, like a gold 1 copper 3, gold 2 copper 2, gold 3 copper 1, for example. In this case, for the copper dimer, I'm trying to show like the black diamond, this is the DFT reference data, and also the red one, this is a new network potential. And in this case, also the black diamond or other symbol here to show reference data, and the solid line to show potential energy surface, new network. And after a few iterations that we train, we can see that new network potential can really describe the reference data accurately. Yeah. So conclusion is that a new network can really learn the function between the structures by using by model here. Before I move to applications, I would like to discuss about the descriptors that I mentioned at the beginning already, because there are so many methods that we could look at. For example, like the hidden layer here, many groups that methods. But today, I only would like to focus how we use or how we describe and how we design our descriptor to construct machine learning potential or neural network potentials. So I will discuss how we develop the descriptor here. Just to remind, so the properties of atomic energy here, this is the sum of the each atom in the structures. So we would like to make sure that the atomic energy is invariant with, for example, respect to the we exchange atoms. If we have, for example, like a water, H2O, right? We have 2 atoms of hydrogen. If we exchange between H1 and H2, this energy should not be changed because this is the same water molecule. And also the number should also not changing if we have like if we translate or rotate the structures. For example, here in this case, just very simple cartoon. If we have like A, B, and C, and if we change A, B, C position, or even slightly move a little bit, the energy should be the same. So the one that Behler and Parrinello proposed is that use a very simple idea is, for example, 2 types of function that we have. For example, the 2-body function, this is atomic radial distribution function. In this left-hand side, to represent, for example, our atom that we are interested in, this is the yellow one here. And the environment in the R cut, usually we use like a 6 to 8 angstrom. And we sum up of the number of atoms that in this R cut. And then we get the energy for this represent atom here. And in the second part, this is atomic angular distribution. Usually, this is again the same reference atom, the orange, and also we consider the 3 atom in this picture. and they are also, for example, in this case, I use the same R cut like a 6 to 8 angstrom. But typically, like the importance of the angular, we could also use a smaller radius cutoff, because the most important is that like the angle. What Behler and Parrinello use, they use the radial part. They use the Gaussian function here of the two terms, for example, Ri and J, and together with the R cut or the R shift that we have here. In this case, I show you that 6 angstroms, and this is the combination of many different Ri and J in total. This is just to look at the functional form or the graph of the two-body term. And then the second, the angular symmetry function that they have, this is just the combination of the 3 atoms. And in this kind of this curve, I just show very simple that we have in this equation still contain of the Gaussian and also combined with the R cut here, which is many different combination with the 3 bodies, just to see. Okay. Just would like to show you from the experience that I have, the Behler-Parrinello descriptor that we use, and especially for multi-component systems, we found that the Behler-Parrinello that use all kind of parameters that also interact with many different chemical species that we have to list all as the input or the descriptor. For example, in this case, if we have descriptor for 3 chemical species, A and B and C, so the way that you have to describe on your input or before you use it. In the radial part, that we have to have like already AA, AB, AC, which is the number of the descriptor or the symmetry function of radial part. We have like a factor of n. And then the angular for the 3 chemical species, here we have the combination of all 3, which is you will have like the factor of like O n square, which is very, I mean, if you have like a few chemical species, it's easy or it's okay to use it. But if we have many chemical species, for example, like a complex material that I just showed in the previous slide, like if you have like a copper, gold, water, and sometimes you also need to include like ion, maybe like a sodium, chloride, and so many things. Which it, if we would use this type of descriptor, it will be very difficult to describe all of. In theory, yes, you can describe, you can list all of the combination, but in practicals, you will use a lot of CPU to evaluate your descriptor. So we found out that it's very difficult, even we already start to use for more than 4 chemical species. So what to do? I just sit down and think that actually, if we use machine learning, right, and we really don't need the complete descriptor. Because, for example, like a Behler-Parrinello function, actually there are not even complete basis to describe all structural space, because we only have 2D, like a 2-body and 3-body, and which is very simple. And then, but it works so well, like I just showed you in the previous example, even for water or even for copper gold that I just showed. And actually we found out that use machine learning technique actually are useful when we use actually incomplete descriptor that we just checked before. And we know that the descriptor actually does not have, it just need to show the distance between the structures and the coordinate, which is already good enough to show how, some important of atomic arrangement on structures, which is also, we can also use this idea or the same idea to describe also many different chemical species of your simulation that you would like to have it. So we are thinking like then we should construct a simple and also incomplete, but we can use it, the descriptor that can really refinable of the local atomic structures. So I will use now the way of the notation of if we want to use for the descriptor to describe atomic structure, use R, and how to use to describe the chemistry, I just use this notation as a T. Now, a new type of descriptor, which is can use it to describe many chemical species and also to describe the structures in a way like the more number of the bases or number of the descriptor, it will improve the the accuracy of the potential energy survey that I'm going to explain in a few slides here. So the first part, I would like to discuss about the descriptor that describe the structures. Oops. Here, let's think a bit. But still, we know like a Behler-Parrinello, it's simple, right? That you use like a radial and angular. And I think it's already simple and also easy. So we also use the same idea. So we still have the same notation. We still, the new descriptor still contain 2 bodies and also 3 bodies. But how we make it different is that we find a way of the basic function, which is autonomous basis set. Which is, for example, here in this case, we use Chebyshev polynomial for the reason is that like a faster convert. Actually, we also just can use Fourier transform, also fine. What we do is that we have the term of the 2 bodies and 3 bodies, and then we expand the basic function into this function, very simple. Here in 2 bodies, so we have now the parameters that we have. In this term, we call, after the expansion of the basic function here, we have the coefficient, which is also in the way that we use it in also R-cut. And also the same way of the 3 bodies, we also have this similar of the expression of the 3 body, and then we expand in this function, which should make it now for both radial distribution function and also angular distribution function, it is invariant, and we can use it as a descriptor. And this is just a visualize of the Chebyshev polynomial. The previous that Behler-Parrinello used a Gaussian curve, if you remember, but in our case, we use now to describe the structures, we use the Chebyshev polynomial. In the A figure here, this is to show the basic function of the order of, in this case, the 6th order. For example, the black one, this is 1st order. And then the red one, this is the 2nd order, this curve. And then the purple is more complicated here. And the 4th one is the blue one, and so on. In this case, that we have automatically that we can use, the more order that you add to describe your structures is the more complicated plot that you will see here. But for the B here, you can just ignore it. It's just the way the corresponding basis function that we reconstruct the ADF or the RDF here. In the next slides, I will demonstrate how we use our Chebyshev basic number to describe the structures and also how it's improved. For example, here we just make a case. We use the crystal rock salt structures of lithium manganese oxide. This is just for battery materials. And then we just draw the discrete RDF function of these structures, the black plot here. This is the actual or discrete RDF. And the red curve, this is just to show the function cutoff. In this case, again, I use 8 angstrom, as you can see here. So how we will use the descriptor to describe these structures? The B function, the B here, we are using only 50 descriptor size. And then we plot the RDF. In this case, we use, actually, we just make the Gaussian convolute to make it more smoother. In this case, we use like a 0.2 angstrom of this actual RDF of the structure. You can see that our descriptor, about 50 descriptors, can describe already the RDF that we have in a function. And then we demonstrate by increasing number of descriptor to 150. You can see the yellow one here, right? It's more peak, which is, this is the reference that we would like to have. You can see that our descriptor now improving is close to the reference peak that we want to have more, which is the more you add, the more accurate that you want to have. And but the thing is that like how accurate you would like to have. And also the more you add, it's also very expensive if you would like to use as your application. And then the next descriptor that I would like to describe how we include and how we make it with many chemical species. So we also use similar idea of the cluster expansion or icing model that they have if they have many different chemical species or different sites. So they use like a spin up and spin down. In this case, we use similar idea by having this kind of different chemical species by use just simple different number. For example, we have, so we introduce the second set of the coefficient that we describe the structures. In this term, we still have two types of the descriptor. We still have the two body and the three bodies. And now we introduce the, we call weight of the chemical species. The way that we introduce, I mean, this is just something that you use it to classify different type of chemical species. For example, if you have one chemical species, so we use number like just 0 that we use it to multiply with your function that you have at the beginning. And if you have two chemical species, we use like -1. And if you have three chemical species, we have -1, 0, and 1, and so on. That you can get the information that you have different type of chemical species. Even you have one chemical species, right, and you have 0, even you get the number of your second set at the 0 information, right? That should show that this is the one chemical in your structures. And now we also, again, to expand the coefficient and to make it more invariant and also translation and rotation. In this is for the two body term, and also the function cutoff, and also introduce the weight chemical species that I just explained, and also similar to the three bodies. And this is the, we have in like the set of the function that we use to describe the many different chemical species. And for the real descriptor that we have, so we have to combine the descriptor that describe the structures together with the descriptor describe the chemical species. Yeah. And then after we use this, we make some tests of many different type of, include many different chemical species on the structures. On the left-hand side that I show here, this is to describe, again, the rock salt structures, which is contained of lithium and tungsten metals, and also oxygen, like O2, for example. And in this case, we test 4 different reference data sets. The first reference data set, we have 3 chemical species. And the second one is 4 chemical species, and then increase also 5 chemical species and 11 chemical species. And then we do test by increasing the descriptor number that we use. We can see that all sets that we have, the descriptor that we use, it is already between like 40 to 70 descriptors. It's already give quite good, I mean, close to the reference data that we have. In this case, I mean, we just use like 3 millieV as a reference. I mean, the lower the better, but I also don't know which one is the best. It's depending on your application, you have to use it. This is the test data that we have, not included in the training set that we check. And in the same, we also use the same descriptor to describe amino acid that we get also from database. We pick the reference data from that contain 5 chemical species, and also we collect all of the database that they provide. So we have like 11 chemical species that we also check and test how the descriptor that we use it, how many. So we found that around 40 to 70 descriptors that we could use it already. But the way that we evaluate, the more chemical species, it's more complicated. So we use really like a lot of iterations until it's converted to 3 millieV per atom, like 5,000 iterations until we get this accuracy. Yeah, this is just wanted to show you how our descriptor that it can use, and also it also even very complicated, even many chemical species. This also works well. How to construct neural network potential or machine learning potentials. First, I would like to show you, this is just systematically way that we are doing. First, we have like an initial reference data set, and then we do preliminary construct neural network potential. And then we use the potential to perform the real MD simulation, or even in MC simulation that you have. And then you compare your energies with your reference set that you have. And you check if it's already good or not. You can see here, it's not really very perfect. You just compare your structures with your reference data. If it's not good enough, so we will just refine by doing the same and include the structure is with high errors include in the training set, and do it until you get your neural network potential as accurate as you. But again, the RMSE doesn't tell anything, I mean the errors, but it really depending on your application, you have to use it in your application and also predict your properties that you would like to know, that you would like to have. And also, actually, Luca already mentioned that some points that you have to be careful and to look is that the overfitting and also the extrapolation, right? For example, here, I just show a simple the cosine fitting. The black one is the target that we want to have, and the training point is the circle Y, and the red one neural network. So what we can do if it's overfitting, we should also start to introduce some kind of like early stopping, or we can also introduce some kind of include more information. For example, like in this case, we would like to have the good force. That's why we also could use force also for the fitting. And also another point for extrapolation, we have to make sure that what we don't include in the training set, maybe it can predict something that not meaningful. So we could also careful check, and also maybe also introduce some kind of like early warning for simulation. Yeah, and this is just the summary of the first part that I would like to discuss for the theory. So neural network potential are interatomic potential, which is based on neural network. And also the neural network potential now represent atomic energy, which is also describe the descriptor based on local atomic environment. And now it's, invariant descriptor, and also can use it to describe many different type of chemicals. Yeah, I think I will stop about the theory now, and I'm happy to take the actions. Actually, we fit neural network for one neural network, and then we use it in many different type of MD simulation. For example, different temperatures, and then we predict the energy of the structures in each trajectory. For example. No. In our case, we use many different temperatures include in one training set. Again, this is I have to answer in a way. It's depending on your applications, right? You have to know where your application, the range, energy range that you would like to have. For example, like if you would like to study like with low temperature, maybe like room temperature, or maybe you don't need that many high temperature include your training set. The way that we do is that, first you look at where your application, and then you include your AIMD or your DFT in the training set and check if it's already good for what your application need or what you want. Yeah. I'm going also to show in a few examples. I would call it is specialized neural network potential. What I try to talk is it like a general neural network or machine learning potentials. I would say yes, this is a weak point. We need a lot of configuration to make sure that you have the reference data that cover your potential energy surface, which you are right. It's really, yes, that is correct. Yes. We can do if you include the reaction inside of the training set. It can do. Correct, but the way that I explained at the beginning actually is more than 2 or 3 bodies, right? But just the way that we describe the 2 or 3 bodies, this is the initial. But when you have the structure in the local environment, there are more than that. Yeah, and then we combine all of the information as a descriptor. Thanks. organizer said I have to make it quick, so I will really go very quick on my application. So, because anyway, they are already published. You could also follow up by looking at my papers later. Okay, so I hope I could show you how we build up the theory for to construct neural potentials. Just to show you, this is the work that I have done with Professor Behler when I was in Bochum in Germany. So we used neural network potential that could describe such a system size and also looking at like a dynamics. This structure that is a copper zinc oxide, which is a good catalyst for methanol synthesis that we are interested in because it's so complicated. I will just show it as example. The first step that we construct, so I start with looking at like the copper. The copper first, this is just as a benchmark or just to check. This slide just to show the detail of calculation that I just would like to give you an overview, like how much work or how easy or difficult that you would construct neural potential. This I would say this is quite general one. First, I will quick look our reference data that we calculate for the copper structure. We use ABJ-Ames code, and in this case, we use PBE because it can describe the properties of the copper already good enough for our applications. The structure in the training set here, we start from 2 atoms. This is the crystal structures until also nanoparticle or cluster until maximum like 100 atoms in the training set. You see, this is quite small number of atoms that you use it to run the FT calculations. And in this reference data set, we have like a copper bulk cluster and also surfaces. In total here, we have around like 32K structures that we have. And we use also force profitting too, so the information that we have here is good enough. And we used Professor Behler code, is called Runner for neural network fitting. And this is the accuracy that we get with our neural network. In this reference data, we split into parts. We have like a 10% of the structure, which is not included in the training set to check the accuracy of neural network potential. You could see here most of the structure that we have, the RMSE compared to the DFT here is really low, like lower than 1 milli eV per atom, and so on. And then we use neural network potential to compare or to check the accuracy by calculating, in this case, the surface energies. We use many different surface structures here, like a copper 111, copper 100, and also 110. And this is the DFT surface energies, and this is our neural network surface energy that we predicted. You can see here, it's already look pretty close, right? And the second part that we would like to check, we just set up the copper surface 111 and also introduce 1 atom of copper on top of the surface. The distance like a 1.5 angstrom. And then we move that copper atom along this part. And then we check the energy profile. We do this the same time, use the same potentials also to predict also the atom on top of 100 copper surface. You can see like the energy profiles of both surfaces of the neural network really can reproduce the FT energy profile very accurately. And we use neural network potentials also to look at the complex surfaces here, which is this structure that we do around 30,000 of atoms and many different type of environment. You can see if we would like to predict the energy or get information by the FT, this is quite difficult, right? But Aalto neural network potential that we have, we use like a few minutes or only on one core on your laptop that we can predict or can do simulation for this kind of system size. But how can you believe that neural network potential is accurate? We can directly compare the energies because of we don't have the FT energy reference. So we are looking at something like the forces acting on atom that is happening on the surface that we are checking by. We look at some atoms that I just showed before here. For example, like atom 1 to until 12 that we use it, and the forces acting on each or on the atom that we are selected should act the same, even if it's small or large. So we looking at here the atomic forces of atom, the 12 atom that we're looking at here. You can see that atomic forces of neural network and the FT, they are really the same, I would say. So it means our neural network potential here is reliable. And then we extend our potentials, also zinc oxide, and we use it to, in this case, this is just a preliminary results that we use it just to show you that we now have the reference data. This is a lot. I mean, this is the question that we already had before. This is contain a lot of information and also the reference data, including many and a lot of temperatures that I use it to fit the potentials. You can see that here, after a few, not a few, actually around 300 picoseconds, the structure of the copper, actually I made it like a perfect half of the cluster, and now after it's running 300 picoseconds, I look at the structure which is compared with the experimental images from the colleagues from Bochum that they are using like a copper zinc oxide on top of the structure. It's quite similar. I mean, this is just to show you like a neural network potential can use it to really study for really large system size. And the next application that I would like to show to you is that another material that we are interested in is alloy. And in realistics, in this case, the copper alloy is good and efficient catalyst for CO2 reduction. When I was a postdoc, our colleague just came and asked, like, here, can you please help us to identify or to find the composition of the copper gold? Because of, in this graph, we can see that if we use only pure copper, it's oxidized too fast and it's dead in the reaction. But then when they start to introduce or mix like a gold, it's getting better and also stay longer in the reaction. But if you use just pure gold, it's not as good as you have like a mixed copper and gold here, right? So we would like to learn and understand this behavior so that we can also design and modify for the cheaper alloys in the future. So we study for maybe in this picture that they have, this cluster size is around 5 to 10 nanometers. So yeah, my job is that we would like to find the important composition and also find if we can really see what is happening. In this case, I first do composition of copper gold with only in vacuum, not yet in the solution. We just start from the small nano cluster first and also increasing. So we found that the copper like to stay in the core, or even in the gold like to stay on the surface. Actually, I don't show it here, but we also check only the surface energies, and we also found that in vacuum, the gold have the lower or the lowest surface energies. And we construct neural potentials and use it with Monte Carlo simulation annealing. I hope I can show you how our neural network potential optimized. The top one, this is the whole particle, but for the below, it is just the cross section that I have. And this is the Monte Carlo annealing movies that we start from the hot, like a 5,000 Kelvin, and annealing to 300 Kelvin. And this is the results that we get. And we also increase the cluster size. This size is around diameter around 6 nanometers. And we also do the same. We also get the same results here, that gold like to stay on the surface. And also mix copper gold in the core. So I just would like to let you know, this is the CPU time that we can use. I just picked the small nanoparticle 147 atoms. For the FT, we use like 3 hours with the 16 core. But to predict for one Monte Carlo search, it's really very quick. It's just less than 1 second. And for this size, around 4,000 atoms. So the FT is very difficult to use and to optimize the structures. But for new network, like a minute to find the structure here. And we also wanted to make sure, like, because it was just a fixed atomic position first, that we find the composition, and then we would like to make sure if it's really stable at different or high temperatures. So we also use the structure that we got from the Monte Carlo simulation, and then we start to run MD simulation. And yes, at a lower temperature, like 300 Kelvin or 500 Kelvin, we can see still the copper still like to stay in the core and the gold on the shell. But for higher temperature, it's slightly changing structure. Yeah, you can see here our neural potential can also help us to find many different compositions, and only the stable structure that I show on the previous slides that I plotted and showed. This is the first application. And then we use the same potential, also including more chemical species. Now with the water, we also use it and also find the composition in the solution. And this is, we found slightly different results. So with solution, we see that the copper also like to come on the surface, like oxide or try to do some kind of reaction with water. Yeah, and then later, but I don't show it today, we also use the structure. We found also study like how the activities, how good of a different the composition. But just would like to show you how we use machine learning to find the composition of the copper gold. The next few slides, I would like to discuss, which it already question came at the beginning, that how we really construct potential. So I would call now, it's depending on application, right? Yes, usually I would say it would be great if we could do like a general or universal potentials for each chemical species. But in realistic is that each research question, we don't need like a full potential or general potential like that. So what I'm trying to show here is that we also can do specialized machine learning potentials, but use it together with more accurate methods. For example, like after we get the structure or get the result from machine learning potential already, we can use it to verify or to make use it with together with, for example, with the FT calculation. So the first example that I'm going to show is that, again, working with experimentalists or collaborators, they are went to the lab, and this is their example. I mean that they have. It's a copper serial oxide. They ask like, how can they find where atoms sit? Where are copper atoms? Where are serial atoms? And so on. So they really would like to know, because of they would like to find where are the active sites. So they asked me like, can you help to find atomic positions of this catalyst that they have? So, and then I said, okay, we can try. So we start to do the FT calculations for many different surfaces of the copper serial oxide. and also to train and then construct the whoop construction and get the result, and then do Monte Carlo simulation to find where are copper sit or where are the serial atom. The blue one in this movie is that a copper atom. The pink is the stereo and also red is oxygen. So after many different Monte Carlo simulation using specialized neural network potential, only for this application. So we found that the copper like to stay on the surface. And we average the structures after equilibrium already of the Monte Carlo structures. And this is, I think it's around like 20,000 of Monte Carlo structure after equilibrium. We average the atomic position, and we found that on the surface here, this diagram, we looking at the center of the nanoparticle, and then draw it's, see this is 1.8 nanometer. We looking at like count the frequency that we found. We found that the copper like to stay on the surface, but actually not all the time, but also some surface here. And this is the half nanoparticle, and this is the full. And after that, we get this, so we use the surfaces that we use it to train neural network, and we look back, and then we check the structure that contain of this type of structure to look at like how the oxidation of the copper on the surface here. But this is just the FT. Then we can classify how the active of the copper is it like a 1+ or 2+. So, and the next application, this is the amorphous structures of lithium, phosphorus, oxide, and dope with nitrogen. And this is the electrolytes that they use in battery. Usually it's become amorphous after the cycle of the battery, right? So it's so difficult to use the FT because of it's, for the amorphous we need larger structure that we can define how the structure look like. And typically, this is the Li3PO4 or LiPo that they use it as an electrolyte. But they said, or some experimental people, that when they start to dope nitrogen, like 2%, 3% until 8%, it's already become better, improved. But then as here is, so where nitrogen atoms sit. If we use the FT and then try to put and try to get, it will be slightly, it will take a lot of time to do. So we construct a specialized machine learning potential, and then later, after we get structure, we do the FT to check. And this is the result that we get for the, as I said, in battery, so lithium can also can insert and also can remove. So we have like if we remove and also we introduce that percentage of nitrogen, we can see that it is around like a 0.5 EV per nitrogen. This is a nitrogen that we start to dope. And if we have in this line, we also have like around like 0.8 or 0.9 EV per nitrogen atom. This is the formation energy that we get. And this is just the structure that we found from neural network potential, and also from the FT tool. We use it. And once we get the structures from the FT, we use it to run AIMD. This structure we got from neural network potential. And then we use the more accurate method like AIMD to get another property like diffusities and also conductivity. So in many different compositions that we have here, we also found that the same like experimental result that we have nitrogen dope, we get better conductivity than just without nitrogen. In this example, just want to show that neural network potential have to find structures, and then we use the structure that we find to a more accurate method. Just like to have for the sampling. The next system that I'm going to show is that like a lithium silicon, and this is also used in the anode battery, which should also become amorphous. In these pictures, or on the A picture, this is the general or the full Nongnuch potential for lithium silicon. But on the right hand side, this is only the structure that we generate and use it for the structure which is close to the ground state structure of the composition of lithium silicon. This is the composition of lithium and silicon in many different compositions. On the yellow one, this is a new network prediction of the Hall. And actually, you don't see the black one. This is a DFT. So new network predict and find the right ground state as a DFT. But I just wanted to show that in the new network, spatial new network potential, we can already use it to predict some kind of like a result that we can use it already. For example, in this case, we use only the region that I just pointed before in the B picture from the previous slide. This is the amorphous lithium silicon that we get from a new network potential and recalculate with the DFT just to make sure that it is correct. And then we compute the voltage curve here. From the experimental data, it is like the blue one. And this is the average. Our prediction is on the green one. You can see for the amorphous structures. And the black one, this is for the ground state structure that we see. So you can see that we can use neural network potential to guideline and to get the structure already close to experimental data. But if we have to use and find the composition here with the FT alone, it will take a lot of time to search and to find it. And we also extend the data, and then we also make it like a general potential. And before we use it, we have to make sure that the potential is accurate. So we would like to use it to study like diffusities or the, we have to make sure. So in this case, we'll check by looking at the NEB calculation with many different channels. And this is just to show example that in this different composition, they already really can get accurate results. And then also we use in MD simulation, in this case like a very long MD trajectory. And all that also not include in the training set. I mean, the FT and neural network potential like predict, I mean, is the same accuracy. And we use it to study many different types of structures of the lithium silicon nanoparticles and also in the structures. So, I mean, just in case you are interested in on this work, I think just would like to show you is that neural network potential can use to study such as system size and also very complicated, and also in the same time in many different compositions. But I think I don't want to discuss more about the science here. Maybe you can also read in detail here later. It looked like it's already time is up. But at the end, we should always compare our result that we get with experimental value if our result that predict is really makes sense and also accurate. It's just my conclusion for the second part. But what I would like to is that like the outlook. Actually, we need more systematic tests that we need, and also we would like to mention that the transferable of the format of neural potential should be easy. But there are so many groups also work and many codes. We should make it like a standard format and also work it or for people that would like to use it. And also for larger chemical and also configurational space, it should be easy to use. And maybe we could also introduce some kind of physics, a new network way to use. And I mean, at the end, like we should also have the potentials, and then we also should share with everybody, and we should also use it and also improve. Maybe it's better for the community. We also try to do this, and also try to share with the community that you don't need to do the same material or the same potential that we have already, just to work together and also to share data. Yeah. At the end, I would like to thank the people who used to the work, and also to help me to get everything done here. Now in Columbia, I'm collaborating with Professor Shen, Professor Urban, and also Dr. Hyberson at BNL. Also in the SEDA group that I also gave a talk, and also talk about LiPoN and also lithium silicon, like Professor Seder, and the group also at MIT about copper, gold, and also copper series oxides from Kalpa group at MIT, and also with Professor Behler when I was in Bochum. And also thanks for the computer resources from Exceeds, and also many collaborators that have to use our code, and also help to suggest and improve. And also thanks very much for your attention and also the invitation here.
Any applications? Any questions? Thanks for a great talk. I wonder to know that how transferable neural network potential is, or how sensitive is to the specific of the system.
Actually, again, it's depending on your application, right? In our case here, like, I mean, what do you mean how, for example, I construct the potential for lithium silicon, right? That I have it, and we use it only a small number of atoms, like I said, 3 atoms, or even 100 training set. Use one potential to describe like nanoparticles and many different compositions, and also can use it for bulk structures. And if you would use, for example, like the molecules, right, which if it's not included in the training set, this will still have to be checked still, yeah.
Well, if you train your potential, for example, water and surface, and can you use that potential for bulk water, for example?
You use only the surface, no bulk, right? But in the surface, you already have some information of the bulk, right? Then you also have some bulk information on the surface. I mean, like to some extent, yes and no. I mean, yes, you could do because you have similar environment already from the descriptor that we described. In the radial cutoff, like in 8 angstrom, have similar behavior, but no in the sense like if your descriptor, like you have the surface, it's like you have air, right, or vacuum, and you have the surface, which is this type of descriptor that you use it in the bulk. You don't have it. I mean, this still have to check.
I saw that you already did a good job with just the energies. Would it help if you, in addition, add the forces when you do the molecular dynamics calculation?
Yes, yes, yes. It will help, yeah.
But you didn't include it in this case.
In this case, we don't use it because we already have a lot of configurationals in the training set, which is already capture the, the energy that we would like to have it. But you are right. Yeah, having forces is very important to have in the training set.
And second, what will be the advantage of your method if you compare with a normal cluster expansion, as long as you fix the lattice that you are working? Because I don't think you are working with a amorphous system, right? In
LiPoN?
Like, for example, copper gold, you have a fixed lattice where you are working, or?
I have average lattice. At that case, I have both. I have fixed to search the configurational by having nanoparticles, but I also use it, the structure, to run MD simulation. second slide that I show. Here. So we can use cluster expansion to have it because of we also want to make sure that our nanoparticle in higher temperature also work correctly. Yeah, in this case, you are right. Even if I just fix case, right, that you could use cluster expansion, but this is not what we want. And this is nanoparticles, which it, I mean, like we will use it in high temperature. So that's why I decided to use new network potential, because we would like to use it at a higher temperature, which it will change the structure at the end.
Okay, thank you.